All good?
Yep.
Okay, so we're going to do isomers. Okay, isomers in total, right? Supposedly, there are two main types of isomers. The first part is what we call a structural isomer. The structural isomer. And then the second type is what we call a stereoisomer. Okay, so what's the main difference? Structural is all the structure, that means structured. But before we jump straight into this, what's isomers? Any idea?
Oh, no.
Okay, so then maybe we need to explain further. Then, are you familiar with homologous series and organic chemistry?
I heard about them before, but I don't remember them.
Okay. Of course you don't, because you're no. You know why?
Why?
Because the year you graduate was COVID and they totally removed the last chapter. That's all the organic chem gone.
Oh,
Yeah, that's it.
okay.
You sure it sounds you okay? You sound a bit sniffly.
Yeah, I'm okay. I just
Okay.
was, yeah.
Okay. So then before we jump straight into that, then it's a bit too much. We really have to give you background information. Okay. There's something called organic chemistry. Okay. What does the word organic reminds you? In general, in real life.
Natural.
Yes, you're right.
Natural.
You're right. So organic
Oh my
chemistry is basically natural chemistry. Originally, right, organic chemistry was invented by the inventor. The person who came up with organic chemistry wanted to use chemistry as a way to study everything in real life that is alive. But in this case, it's not so much of biochemistry, because biochemistry talks about things like enzymes, proteins that are already in the body. Organic chemistry also extends to things that is dead or things that are made of living stuff. The unique thing about organic chemistry is they used to always, most of the time, have what we call a carbon backbone. It's as if the spine of the molecule is made of carbon, and then we attach a bunch of different hydrogens. It will look something like this. So
Okay.
organic chemistry, right? Usually is made of there will be a bunch of carbon, there will be a bunch of hydrogen. Sometimes there will be oxygen, but the primary main thing is basically what we call a carbon backbone. So we call a carbon backbone. Sometimes your professor will also bring up the concept called hydrocarbons. This term is very straightforward. The word hydro here refers to hydrogen, and obviously the term here carbon refers to carbon. So hydrocarbons are usually molecules made of only hydrogen and carbon. Nothing else. So organic chemistry has a little bit more wide definition. It can be carbon, can be hydrogen, can be oxygen, and sometimes even can be chlorine, fluorine, etc. Whereas if the term is just hydrocarbon, then it only has hydrogen and carbon, nothing else. Okay. So in this case, why? So I'm giving you a quick rundown. Why is it? So long time ago, there's a bunch of stuff like dinosaurs and big plants and stuff. I mean, I can't draw a dinosaur, so I'm gonna draw a big dead titan or something, a big human.
Okay.
And then there's a bunch of plants. Okay, so after they are all dead, they are all underground. They turn into this black bluish thing, and this is what we call crude oil. Crude oil, obviously, are basically dead stuff turns into it. We call them fossil fuel. But fossil fuel and crude oil refers to the same thing. Until human invented the steam engine, we realized that we have to find ways to, power the steam engine. So they tried to drill the ground, and then the crude oil, they found crude oil and sprayed out. So what happened to crude oil is, crude oil is basically a mixture. It's a mixture of a lot of different things. So what they do, they basically take the mixture and they do fractional distillation. So what they did,
I learned that, right? Sorry, my KB.
Okay, so you take crude oil, then you do fractional distillation. So what is fractional distillation? Fractional distillation is to separate component in
different body points, right?
Yes, mixture
Okay.
due to different boiling points. Okay. So what happened is the crude oil can get separated into a bunch of things. I'm not sure about at poly level, but in O levels you're required to know what are the products that can be separated. So I'm going to briefly bring up. So it will be the method to remember it. I use Peppa Pig never kisses dirty looking boys. So Peppa
Oh yeah, you told me this before.
Pig never really kisses
Yeah.
dirty looking boys. So which means that this is going to be petroleum gas, petrol, naphtha, kerosene. Kerosene has another name called paraffin.
Okay.
Diesel, lubricating oil, and bitumen.
Oh my god, this is such flashbacks of N level. Okay. Oh my goodness. Okay.
Yeah, because back then we were at the cusp of whether they got to cancel or not cancel it, so we teach the beginning, then it end up removing it. So it was not covered at all in the end. It didn't come out for test.
Yeah, I didn't.
Okay. Okay, so crude oil, in short, is basically part of the original reason why organic chemistry becomes such a thing. Because before that, no one cares about organic chem. It was just some niche study about like natural stuff. But once they realized, hey, you can become a bajillionaire taking this crude oil thing out of the ground. And this crude oil thing comes from all the living stuff dead and then turns into this. And then let's basically use organic chem and basically find ways of making this into different things. For example, plastics. Everything in plastic is made of crude oil. Other than that, of course, all the different jet fuel, your petrol for cars, for lorries, for buses, for aeroplanes, your cooking gas, and even most of your cosmetic products, your lipstick, your hand cream, your moisturizer, anything that is oil based can be taken from naphtha. Yeah, it makes you a bajillionaire. And they found ways to basically just purify this, and then organic chem becomes this really ultra popular thing that people study. And this
Okay.
during the 80s, everyone was rushing. I mean, if you ever study engineering, people ask you to study oil and gas, as in to go into this, or go study
Mhm.
silicon, as in anything to do with semiconductor to make silicon chips. Both of them back then,
Mm.
you can make equivalent of like 10-20K a month. Yes, and even you are not wellly educated, you can actually learn how to operate the equipment. And that means you get trained to be very good at running equipment on the oil drill rig. You can get easily paid until like almost 10-12K as well.
Oh my God.
Yeah, it was insane. It was during the time that everyone was busy digging oil, and everyone back then, everyone that studied engineering will tell you, you go. At least when I was in school, they go like, you want to study oil and gas? You want to go into oil and gas industry or semiconductor? That's where all the gold rush. But it's over now. Singapore, the industry don't mint that much money now, because everyone wants to go into the green industry now. So yeah, so that's that. Okay, so out of all this organic chemistry, right, they introduced a bunch of things called homologous series. Homologous series, right, is like, you know, in the animal kingdom, we try to group animals based on things like mammals, amphibians. So
Yeah.
we give them things, we try to group things. It's just like maybe in like among humans, we try to group people based on race: Chinese, Malay, Indian. Then how do we group people accordingly? Usually, it's based on what? Based on physical looks, culture. Different people behave differently and look differently. Then we group them according, and we name it, and those are called race. Homologous series is like the race, the types of organic chemistry model.
The categories.
Correct. You can understand it as categories. Usually, homologous series, the typical one would be something like alkane, alkene, alcohol, carboxylic acid.
Aren't these functional groups?
They are not. They are not functional groups. They are homologous series.
So what's the difference between functional groups
Okay,
and homologous series?
then slow down. We'll get to that. Slow down. So in this case,
Okay.
what defines a homologous series? That means number one, they would normally have similar naming. Their methods of naming will be similar. Two, they will have same general formula. Three, they will have same functional groups. And four, they usually have similar chemical properties. So based on these four criteria, that's what a homologous series shares.
Are these properties the same as isomers?
No. Isomer, it's one of the... without all this foundation, jump straight into isomer is a certain death. You don't know what you're talking about. Yes.
Okay.
That's why I thought you wanted to know about isomer. I went straight in, but then I'm like, huh? The foundation's not like this thing. Okay, we're gonna die. Okay, so I need to build all... We need to speed run the foundation first.
Okay.
Okay. Are you good at figuring out the naming? Or is your totally blank sheet? I'm not sure.
Blank. I'm a blank sheet of paper.
Okay. So in this case, we will need to go through... We'll need to go through this based on... Okay. So the first thing of the homologous series, there will be a bunch of things. It's about naming. Okay. So when it comes to naming, let's say now we have something called propane. All names, right, has what we call prefix and suffix. Are you into like D&D, like Dungeons and Dragons and role plays?
No.
Okay. Because some people play board games with that, then they know. Or else, prefix and suffix just means that there is a means it's the first part, and then a suffix, which is a back part. Because originally, when in games, right, sometimes they tell you like I can't think of anything. Maybe something like what a bravery wand of fire. So that means bravery means it adds some stats. It gives you additional strength. Wand of fire, then fight. So there's prefix and suffix. We add words before and after certain something to tell that the item has certain property. So prefix tells one thing, one property. Suffix tells another property.
Okay.
So the prefix, right, the front of the name always tells us about the number of carbons. And then the suffix at the back always tells you the homologous series. So in this case, if something is called okay, so in the front, right, since it's number of carbons, this one will be, if it's math, F, pro, but. So math means 1 carbon, F means 2 carbon, probe means 3 carbon, but as in but means 4 carbon. Anything more than that, you know, pentanol, like pentagon, like this is all math already.
Yeah.
Pentagon, then hexagon, heptagon. So let me check something. Okay, so hex, hep, oct, like octopus, oct. So of course the rest continues, but the most important, in my opinion, is you have to remember the first 4. 1, 2, 3, 4, because there has no pattern. The back one, if you know your math, pentagon, hexagon, heptagon, octagon, you can figure it out. The first 4 of MEPB, right, is the most commonly asked, but it's also the most hard to remember. I remember using my math. I use it personally. Monkey eats peanut butter. MEPB.
Okay.
So it's like 1, 2, 1, 2, 3, 4. Monkey eats peanut butter. Whereas on the homologous series end, if it ends with A and E, that means this thing is an alkane. If this ends with an E and E, this thing is an alkene. If it ends with an OL, it's a alcohol. It ends with a OIC, it's a carboxylic acid. So now in this case, that is actually why we say all things ends with A and E are all alkane, and all alkane will have the same homologous series.
Okay.
Okay, so
Sorry, can you repeat that again?
don't worry about it. What I'm trying to say is like A and E, everything ends with A and E. Same homologous series. That's why I said same homologous series has similar naming. Because the
so
back
all
part
A and
hints
Cs
to
are
you
alkane.
what family it belongs.
Okay.
Okay?
Yeah.
So in this case, then number 2, later we will revisit to this, but now I need to reintroduce a new character to the idea. Number 2 is what we call a general formula. General formula is basically a predictable pattern in a certain molecule. So there's a few things, like for example, all alkanes will have the pattern of CnH2n plus 2. Then you have your alkene, which is CnH2n. You have your alcohol, which is CnH2n plus 1 OH. Then you have something of your carboxylic acid. This is a bit tricky, but it's more like Cn minus 1, H2n minus 1, COOH. So what are we trying to achieve? With point one and as in point one being the naming and point two being the general formula, you need to achieve a scenario where if they give you a formula, like for example C6H14, this is the formula. They give you a molecular formula. You need to be able to figure out this is actually the monkey eats peanut hex. So this one is basically hexane. You figure out the name. So this is what we are trying to piece together point one and point two to achieve this outcome. So how do we do this? So let me demo. Now let's say now you have something called C2H4. So since you have 2 carbon, the front is meth F. So this thing must be F, ETH. So that's the first thing. Now we go second thing. Carbon is 2. Then it becomes times 2, become 4. That means that it behaves more like an alkane because N then times 2. So this thing is clearly an alkene. Alkene.
Okay.
Therefore, this is a ENE. So the full name is called ethene.
Okay.
And the opposite is true. If I give you something called propane. Monkey eats peanut. P is basically 3 carbon. ANE tells me that the formula should be CnH2n plus 2. Means times 2 plus 2. Formula should be C3. 3 times 2, 6. 6 plus 2, 8. And you have this.
Okay.
So piecing together your ability of naming and understanding general formulas similar in the homologous series allows you to come up with, from name you can get formula, from formula you can get name. That's your base absolute foundation ability. So far okay?
You lagged.
Okay, so what I'm trying to say is, in the end, what you need to do is to piece together point 1 naming, point 2 general formula to achieve the ability so that you can read molecular form. Give you molecular formula, you can give me the name, or I give you the name, you can give me the formula. That's what you need to have. That's the absolute foundation. If you can't tell what you are reading and you can't name and you can't write formula, die. You couldn't even write your alphabets, you cannot learn English. It's equivalent to that.
Okay.
Yeah. Okay? Like I say, all this thing is a speed run to get to where isomer is. So I am giving you a basic thing, but eventually we still have to practice questions and stuff.
Yeah.
So coming back to this, we are at 2 things. Number 1, we mentioned about the naming already. Number 2, we talk about the general formula. So the third one is on functional groups. So what are functional groups? If naming is basically like a race of people, like Chinese surnames Li, Tan, then sometimes knowing the name tells you it's a Chinese, or Malay is like bin something bin what, something bin ti. Whereas it comes to Indian, something anak lelaki, anak perempuan. So it's, in this case, the name tells you the homologous series. Just like name tells you the race. General formula is more like basically the representation of things in chemistry. The formula tells you, and basically general formula dictates molecular formula in terms of certain patterns that it follows. So number 3 is about functional groups. Functional groups is equivalent to how something looks. So in this case, we have something called functional groups. Okay, are you familiar with what's called structural formula?
Yeah.
Okay, so functional groups are specific things in structural formulas that it's like a certain pattern, certain special feature something looks like. So in this case, if I have something like alkane, the functional group is everything should be carbon-carbon single bond. If something is a alkene, that means everything should be there should be a carbon-carbon double bond somewhere. If something is a alcohol, it should have a OH, what we call a hydroxyl group. And finally, if something is a carboxylic acid, you need to have something called a COOH. It's also what we call a
Wait,
carboxyl
so functional
group.
functional group is how the structure looks like that.
I give you an example. If something you have like this 1, 2, 3, 4, I won't fill in the hydrogen. In this case, all the carbons are single bonds. Due to how this looks like, this is going to be an alkane. Whereas if I something goes 1, 2, 3, 4, something like this. This thing has one carbon-carbon double bond. This is going to be an alkene. And then if something goes 1, 2, 3, 4, it has an OH, and then all the other are filled up with H's. You have a special hydroxyl group at the corner. This will behave more like an alcohol. And of course, you have C, 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 double bond O, O, H. And this one becomes a carboxylic acid. What they're trying to say that in homologous series, all things contains certain pattern. In this case, alkane has the carbon-carbon single bond, alkene has the carbon-carbon double bond, alcohol has the OH, and carboxylic acid has the COOH carboxyl group. Okay. So, and in the very beginning, every molecule can only have usually just one functional group, but a molecule can have multiple functional groups combined together. Then you can have multiple different reactions. That means like something contains hydroxyl group and carboxyl group at the same time. So it has a combined chemical properties of behaving reacting like alcohol and behaving reacting like carboxylic acid. That's eventually you mix and match different things, then you get into things like pharmaceutical stuff where they give you some really complex thing and then you see what are the functional groups.
So chemical properties are determined by the functional groups.
Yes, you can say so.
Okay, is it determined by the homologous series also?
Or rather, looking at the functional group tells you the homologous series.
They're interconnected.
Because eventually it's not so straightforward, you see. In the learning stage, you will see hydroxyl group and then you say, oh, this molecule is an alcohol. Then you see the carboxyl group, this thing is a carboxylic acid. But eventually they start giving you molecules with a hydroxyl group and a carboxyl group. So it's not quite an alcohol, it's not quite a carboxylic acid. It's a hybrid. It has both. So you don't categorize them either way, but then is to study, you basically look back to how alcohol reacts and how carboxylic acid reacts, and then you predict the combined outcome.
Okay.
So that covers functional groups and how things look. Chemical properties I won't jump in first because our original intent is basically chemical properties. You have a bunch of things like substitution reaction, addition reaction, oxidation, reduction and stuff. We won't jump straight in because our original intent is to basically achieve explanation of what isomer is. So now we have basically something called a molecular formula. And we have something called a structural formula. So in this outcome, let's say now I have something called C4H10. This C4H10, when I draw, it becomes 1 carbon, 2 carbon, 3 carbon, 4 carbon. Then I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is the molecular formula. This is the structural formula. So now we go C4H10. 1, 2, 3, 4. As you can see, although the molecular formula is the same, but its structural formula is different. This is isomer. Isomer definition is...
how do you determine where the branching happens?
I don't... Are you implying that there's a predetermined way how branching is?
Like, okay, you see, right, in the first structural formula, the C's are all in a straight line. Whereas the second one, the C's, there's one C below the second C. So when do you determine where the other C goes? Because it can be under the first C, it can be under the second C and third C, right? Then it can also be on top. So where do you determine the position?
It can be everywhere. That's the screw up part. That's why isomer is difficult. And sometimes certain isomers are not isomers, they are the same molecule. Yeah. So I want you to grasp the idea first. Then you have plenty of practice to draw.
Okay.
Yes.
Do you think isomers will come up for the test?
Definitely. Isomer is the main thing that the last time something called, this is just the beginning isomer. Like I started to say the whole thing. Isomer has structural isomer and stereoisomer. Structural isomer is whatever we just mentioned. Physically different, easy to tell. We go into stereoisomer, it's a totally different level in terms of difficulty.
Okay. I can show you my test paper if you want. I have my test paper with me, but I don't have the answers. My answers to the test paper because the teacher
it's
don't
open
give
book,
us.
is it?
No. It was open book for the first test.
Then how do you get the test paper in the first place?
They give us that after they mark.
Wait a minute. So you did the test and then you got the test paper back?
Yeah.
Okay. I mean,
you want to see it now?
No. I mean, we'll go through isomer as a concept first, because I need you to focus on how to figure out structural isomer.
Okay.
Okay. So now, according to your isomer stuff, you see, there's basically, I want you to focus on the left side branch, structural isomer. So you see, in this case, isomers are molecules with the same molecular formula, but different in a certain way. Most of the time, your structural formula will be not the same.
Okay.
Then, in terms of structural isomer, there's position isomer, skeletal chain isomer, and functional group isomer. For now, we will introduce them part by part. Okay?
Okay.
So in this case, let's talk about something called position isomer. Position isomer is a type of structural isomer. So how we do position isomer is exactly what we just did. It's basically okay. Position isomer is actually more straightforward. So position isomer is basically the position of usually functional groups are different. So in this case, for example, compared to 1, 2, 3, 4, then let's say this has a chlorine, everything else has hydrogen. Now I shift it to 1, 2, 3, 4, I shift it to front. In these two situations, they are called position isomer. Why? Because the position of the chlorine is different between the two.
Okay.
So that's the concept of position isomer. We will need to spend we will need to spend time to talk about naming something extensively on another lesson. But for today, because I only teach you the absolute basic in naming thing, in basically the propane. That eventually there's still a bunch of they are called IUPAC naming. That one I totally didn't teach you. We skip that because I want to introduce the concept of isomer first, so that we can actually go into details on how to tell something is isomer and then the name difference and stuff. I'm giving you a basic idea first, or else you get quite lost. So I'm giving you the big picture first.
Okay.
So this is position isomer, position of a functional group. Because previously I just go straight into position isomer is the position of a functional group being different. Then number 1, you don't know what isomer. Number 2, you don't know what's this CCC thing. Number 3, you don't know what's functional group. You are watching a movie right there in the center, you don't really know who's the character. You're gonna die. Now we are speed running, giving you filling up all the character, but we don't have the backstory yet. That's the current situation. Okay, so position isomer is where functional group in a particular organic molecule is different. So in this case, same. So this one will be 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have C4H9Cl. You have C4H9Cl. Looking at just the molecular formula, you tell no difference. But looking at the structural formula, you see the position is different. And sometimes in manufacturing things like medicine, this could be life and death, because it might react with the cell differently.
So the structure of the molecule Okay. Because you like, so I exited it.
Okay. So you're saying?
So does all structural isomers have the same same molecular formula but different structural formula?
Yes.
Okay.
So the shape of the molecule is always different. It's just how is it different. In this case, there are 3 ways of being different. The first one is position isomer. The second is what we call a skeletal chain isomer. So, skeletal chain isomer.
Oh no.
Skeletal chain isomer is where the skeleton is swapped, like for just now what we said. C5H12 Okay. Yeah, I see your message. Okay, sure, no problem. Okay, yeah. Use the washroom. We'll be back. Yes, I know. Don't worry.
Hi, sorry.
Hey, okay, you're back.
Oh no, it's still lagging.
Hmm?
Wait, it's still lagging. I cannot see you move, but I can hear you talk.
Okay, let's see. What about now? Okay, let me do something to it. Better?
Yeah, better.
Okay. So, like I say, there's something called skeletal chain isomer. So, skeletal chain isomer is what I said just now. I will only draw the skeleton of the carbon, with the carbon in a straight line, or when the carbon is being drawn in something like 1, 2, 3, 4, like this. It's being drawn as 1, 2, 3, 4, 5, like this. As you can see, the main skeleton of the carbon totally swapped. And this case called skeletal chain isomer. So it's very different from the previous one where it's just the functional group shifting around.
The functional group doesn't affect the carbon backbone.
Yes, it's only the shifting of functional groups. Agree?
Okay, wait, huh?
Okay. Then the next thing, in this case, sometimes they will draw lines like this. It goes 1, 2, 3, 4. You know about this one?
Yeah.
You know you know how to read, right?
Yeah.
Okay, that's good. So this one should be something like this. 1, 2, 3, 1, 2, 3, 4. Then maybe this one draw out one line. Then this one should be something like 1, 2, 3, 4. So this is represented. Okay?
Yeah.
Sometimes they might even draw things in what we call aromatic, means in a ring. Like for example, you have something like C4H8. In this case, it goes carbon, 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 carbon. 1, 2, 3, 4, 5, 6, 7, 8. And you can have something like carbon, 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 carbon. Yeah, so ring structure is a thing. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so
yeah.
Last but not least, we have something called a functional group isomer. So functional group isomers, right, is different from positional isomer. Positional isomer, you just shift the functional group only. Functional group isomer, right, is something like, for example, this is something is C2H6O. Let's say in this H6O. In this case, that is I draw, it goes 1, 2, OH, 1, 2, 3, 4, 5. So in this case, when I draw in this way, I get 1, 2, 3, 4, 5, 6 H and 1 O with 2 C's. In this case, because of this OH, this behaves more like a alcohol.
Okay.
Whereas if I were to basically draw it in C, O, C, it goes 1, 2, 3, 4, 5, 6. I get the same molecular formula, but now I have a oxygen smack right in the middle. This behaves more of like an ether. So this is another homologous series that we eventually will introduce a full list. As you can see, functional group is totally different. This is an OH and this is an O stuck in the center. In this case,
yes, different functional group, same molecular formula.
Yes.
Okay. So that will change the chemical properties as well.
Definitely.
Okay.
Okay. So in this
Changing
case,
wait, on the structural isomers, right? Does it change the chemical properties? Positional isomers don't, right?
It's a yes and no, because if you just ask me, does isomer change properties? Answer is sometimes yes, sometimes no. It depends. Because it really
depends on which portion of the categories, is it?
Correct. Because there's so many categories, which coming back to this is where we originally first started. Structural isomer has number 1, what I call positional isomer. Number 2, skeletal chain isomer. And number 3, functional group isomer. And structural isomer is where you see there's an actual arranged differently in atoms. Whereas if you go into stereoisomer is more of a spatial arrangement difference.
Okay.
So it means that in this scenario you have quite a different thing. So you have something called geometrical isomer. You have something called so the first type is a geometrical isomer. The second type of isomer deals with something called chiral carbons. And then the third type is what we call a conformers. And this is the part that I told you that it will get a bit more confusing, because you will start you start getting, there's a lot of new words invented. Okay, even under chiral carbons, there are a few types. So the first type of with chiral carbons will be enantiomers. E-N-A-N-T-I-O-M-E-R, enantiomers. The second type will be called diastereoisomer. And then the third type will be what we call meso compound. That's why originally I say understanding your left side is the easy one. The right side, it's challenging. Today the aim is to give you an idea first. before we jump straight into the details. So to give you an idea the difference, let me show you pictures. At least the next lesson when we continue on, right, you have an idea what we are talking about, so you're not lost. So, but structural isomer very clearly is basically obviously the structure of something is changed. That's why what we said. Chain isomer, the skeletal chain isomer is a chain change. Position is a functional group swap. Functional group isomer is like totally different functional groups. But when you have something called stereoisomer, you have stereoisomer is like this. This is something called cis-trans isomer. We will talk about this later. Like, can you understand? In this case, you see the chlorine. In this case, is on opposite direction, but in this case, it's on the same direction. In this case, you realize in this case, stereoisomer plays with things like mirror image or rotation or twisting. Because can you imagine in this case, originally it's like this. This is like a piece of rubber band. Then what happened? It goes twist, and then suddenly the chlorine is on opposite direction already. The position or the chain or the functional group, nothing changed. All it ever did was rotate, twist, mirror image, etc. That's what we call spatial difference. That means the space, such as from what angle you're looking at, mirror, twisting, causes the differences. And they are no longer directly atom arranged differently. If the atom is arranged directly differently, we call it structural isomer. When the spatial, as I said, this one, chlorine, chlorine, twist, then you get chlorine, chlorine. You see, now you're twisting. You didn't rearrange anything. You only causes it to twist differently. Or when if it's double bond, you can't twist. So now, how do you call this and this when technically this is the position, chlorine position 1, chlorine position 2, chlorine position 1, chlorine. Then how do I mention to the reader that my space is where the chlorine on the same side or the chlorine on the opposite side? Then you have to reinvent things of like cis, trans, and all these terms to talk about them spatially arranged differently. Those are called those are basically called stereoisomer.
Okay.
So that's the general idea. That's the general idea why this is easier to understand. This is harder to understand because you have so many types of. It's more abstract. Maybe that's rather than using the word more difficult. It's more abstract. You need to think and rotate things in your head, and to see it from different angles and stuff.
Oh, I cannot visualize it.
Then never mind. There are tricks to basically cheat your way. There are tricks to make things easy.
Oh,
you don't have to rotate the thing and all the time. There are easy ways to be a crutch to do it. So for the next lesson, we need to do a few things. Number one, we have to go through something called IUPAC naming. You write this down and then you. Yeah, we have to go through something called IUPAC naming. You can't do IUPAC naming, you're gonna die in anything with chemistry related to biochem, everything you will die. Because you can't understand the naming. I need to teach you the foundation. This is where we need to dive deeper into. So IUPAC naming is required. Number two, we have to figure out how you draw isomers and how do you isomers versus same molecule. In certain situations, two things may look like isomer, but it turns out to be the same molecule but just viewed from a different angle. I mean, it's just like, for example, when you look at me like this versus you look at me like this, according to the computer, they say there's two different pictures, therefore two different persons. That's not true. I merely rotated my face. So in isomers, there are certain situations.
Isomers are not the same molecule. It's just the same molecular form. molecular formula.
Yes, but there
Right.
are special situations that I can use the same molecule, twist and turn a certain way to trick you thinking it's isomer.
Oh, okay.
And without knowing the IUPAC naming, you can't tell this efficiently. It's all
Okay.
linked together. And then once this two thing clears, this side fully clears. Then we have to then dive deeper into the different types of stereoisomer.
Okay. Will you prefer me to read up on my notes before attending the lesson?
I would say, does your school ask you on like any textbook to read, or because your notes are very
No.
brief?
Yeah, I'll just